If j and k are integers and j minus k is even, which of the following must be even? An even number is a number which can be divided by 2, and an integer or whole number result. So here are some examples. 2 is an even number because 2 divided by 2 is 1, which is a whole number and integer. Negative 4 is an even number because negative 4 divided by 2 is negative 2. A negative number, but an integer nonetheless. Negative 888 is an even number because negative 888 divided by 2 is negative 444, a whole number. And 0 is an even number because 0 divided by 2 is the integer 0. Now that may seem awfully trivial to a lot of people, but I don't know where anybody who is watching my video is at mathematically, so I put it in there. But these are some facts that you might not know. You might not know that every time you take an even number and you add an even number, you get an even number. Furthermore, if you take an even number plus an odd number, you always get an odd number. If you take an odd number plus an odd number, you always get an even number. And another thing that might be helpful, or another set of rules that might be helpful for this problem, is that an even number times an even number is always an even number, that an even number times an odd number is always an even number, and that only in the case when it's an odd number times an odd number do you get an odd number. You might have noticed that I did not put a subtraction or division version of these rules. That's because subtraction and addition are two sides of the same coin, in the sense that subtraction is just addition with negative numbers, and division and subtraction are two sides of the same coin, in the sense that division is just multiplication with reciprocals. You would find that the rules are actually very similar. Now, if I know these rules, and I know that j minus k is even, well, there are two situations here where I get an even number from something resembling addition, like subtraction. Either both are even, or both are odd, okay? Which means it need not be the case that k is even, since both could be odd. However, what about j times k? Remember, either both are even, or both are odd. If j and k are both even, then we have from here that even times even equals even. If j and k are both odd, then we have from here that odd times odd is odd. Therefore, it cannot be b. Now we'll have to go down a couple of layers. What about 2k? Well, 2 is an even number. Now, every time we multiply an even number by 2, it must be divisible by 2. Also, see here. Even times anything winds up being an even number. That means that this is definitely an even number. Now remember, j at this point could be even or odd. Wouldn't matter what k is, because this is always even. Well, if j is odd, then by this rule, we have that this thing would be odd. Therefore, it does not have to be even. Now I'll say it again. Either j and k are both odd, or j and k are both even. For option D, consider the case where they're both even. Well then, j times k is even times even, making this number even, and j is even, which means this is even plus even, and from this you must get an even number from this rule. But consider the case where they're both odd. See, now this is odd times odd, which is definitely odd. But this is odd, because both are odd. Well, now that means that this is odd plus odd, but by this rule, odd plus odd is even. We have shown in both possible cases that D must be the answer. This will always be even. You may be wondering where the plugging in approach is concerning this problem. And it's there, It's just that you have to realize that there are two versions of this you have to do, and you might want to make them distinct from one another. You have to be aware that one way of doing it is to say that both j and k are even. You could say that j equals 4, for instance, and you can say that k is 2. Now this is within the constraints of the problem, but you'd also have to know that an odd plus an odd is an even 2, or an odd minus an odd. Again, subtraction, addition, not really different things. So you would also have to consider a case where j is equal to, say, 3, and k is equal to 5, and then you would have to run the substitution on each of these things. Judging from this, there is one option, read this one within the constraints of the problem, where k is an odd number, so it can't be that one. If you go with j times k, in situation 1 it's even, but in situation 2 it's an odd times odd. It's 15. If you go with, don't remember what that said anymore, there we go. If you go with j plus 2k under situation 1, you have here 4 plus 2 times 2, which is an even. But if you go with situation b over here, you have 3 plus 2 times 5. You have 3 plus 10. That's 13, which is not even. Now if you get down to jk plus j, you have 4 times 2, which is 8, plus 4, which is 12 under situation 1. And in situation b, you have 3 times 5, which is 15, plus 3, which is 18. And it works under that situation. It works under both. Okay, so the plug-in method is there. I don't think there are too many pitfalls here. I wouldn't use 0, okay, and I wouldn't use 1, just as a general rule. But as long as you remember to try both of these methods, both of these things that make this true, then you're good to go. But honestly, you'd kind of have to know these rules anyway, right? Or you'd have to do some quick guessing and checking to see if you could get all the permutations of j minus k that make it even. Honestly, I don't think it's too much of a stretch to go the first method, the more abstract method, if you're already familiar with these rules.